Welcome back. Today we are going to talk about the evolution of AI learning paradigms. You might ask, why learning paradigms? Well, simply because the artificial intelligence has made astonishing progress in recent decades, and much of that success comes from how AI learns. Understanding AI learning paradigms is important because it sheds light on why modern AI systems work so well and how we can make them even better. Interestingly, many AI learning methods are inspired by the ways humans learn, from being taught by a teacher to exploring the world on our own to even learning from trial and error. By drawing parallels to human learning styles, we can more intuitively grasp these concepts and appreciate their evolution. AI researchers often talk about three core types of machine learning, which have been around for decades: supervised learning, unsupervised learning, and reinforcement learning. These are considered traditional paradigms because they were among the first learning styles to be studied in AI. Each paradigm answers the question, how should an AI learn from data or experience? And each does so in a different way. To make things fun and easier to understand, we will compare each of these to an analogous way that humans or animals learn. Let us start with supervised learning. Supervised learning is often seen as the most intuitive learning paradigm, almost akin to how students learn in a classroom. In this approach, an AI model learns from input data that is clearly labeled. The training involves a teacher providing correct answers, enabling the model to generalize and make predictions on new data. This methodology is effective due to its reliance on established outcomes, ensuring that the learning process is structured and purposeful. Now let us go through some historical milestones in supervised learning. Supervised learning has evolved significantly from its origins in 1950s. The perceptron algorithm was an early attempt at creating a neural network. Throughout the following decades, various algorithms, including decision trees and support vector machines, contributed to its development. And the breakthrough moment came in 2012 with LXNet, which demonstrated the potential of deep learning for image recognition using vast amounts of labeled data. You can think of supervised learning as as something where we provide the model with numerous labeled examples. For instance, to train a classifier, we show it images of cats and dogs. The model learns to associate these images with their respective labels, adjusting its parameters to minimize predictions error. And this process is crucial for developing accurate AI systems. In the supervised learning process, the model learns to map inputs to outputs effectively. By minimizing the loss function, the model refines its predictions. The key challenge in supervised learning is generalization, ensuring the model performs well on unseen data, not just memorizing training examples. Supervised learning is integral to many applications in our daily lives, from classifying emails as spam to predicted numerical values like weather. Its versatility is evident. For instance, Facial recognition in smartphones and voice-to-text services like Siri rely on supervised learning models. Additionally, in healthcare, it aids in diagnostic conditions from medical scans, showcasing its wide range applicability. You can take the supervised learning as an analogy of a child learning to identify animals using flashcards. It illustrates how supervised learning works. Just as a child learns to recognize dogs and cats through repeated exposure to labeled examples, a supervised learning model is trained on input-output pairs. This process enables both children and AI models to generalize and recognize new unseen instances effectively. However, AI requires far more examples than a child to achieve similar learning efficiency. Supervised learning relies on feedback to refine its accuracy. Just like how a student learns by checking their answers against a math worksheet, when immediate feedback is provided, it helps correct mistakes, reinforce correct patterns, and improve learning efficiency. Similarly, AI models adjust their predictions based on the feedback from labeled data, allowing them to improve over time. This process, known as backpropagation in neural networks, ensures that the model continuously learns and enhances its performance. By leveraging feedback, supervised learning becomes more efficient and accurate, just as direct corrections help students master complex concepts faster. Ready to dive deep into AI learning paradigms? In part 2, we will explore unsupervised learning and how it differs from supervised learning. Subscribe now so you don't miss it. Like this video if you found it helpful, and let us know in the comments what topics you would like us to cover in the next series.